I'm very excited to present two projects that I've been involved with. They are both shell structures or dome structures. The first one is a project that I was involved with when I was working for Ney and Partners in Brussels, and I had just finished my PhD studies, and I was able to use the algorithms that I had developed during my PhD for the design of an amazing grid shell. So what you see here is an elevation of the Dutch Marine Museum. This is a 17th century gunpowder warehouse. So in the 16th and 17th century, the Dutch were a very good seafaring nation, and they would go all over the world to do business and other stuff. And they would stop at this building to stock up on gunpowder. So this is a masonry building. After kind of the seafaring activities stopped, this building became a prison because it has a lot of small rooms in it. And after that, it became a museum. And so when I was working for Ney and Partners, this museum was being rethought, and the architect really wanted to have a roof over the courtyard. So what you see here is a facade, but actually if we look in plan, this is what the building looks like, right? So there's actually 4 buildings with a courtyard in the middle, and that courtyard is exposed to the elements. These 4 buildings are masonry buildings, so their spans are not that large, and of course they were not designed to take the weight of an additional internal roof over that. So there was an invited design competition was held to design a roof over this courtyard. So that this roof would allow for additional activities like concerts and events to take place in the courtyard. And so we were invited, well, Ney and Partners was invited to submit a design competition. And we based the design on a map that you could find in the museum. In the museum, you know, there's all kinds of stuff that they exhibit, like models of boats and maps. And so this is one of the maps that you can actually find in the museum. It's a 16th century sea chart that shows what the Dutch thought at that moment, what the world looked like. But it also has all these it also has a geometric pattern on that, and so there are all these points. There are actually 16 points. They are wind roses. So the Dutch thought that the wind was originating from these points and then blowing to these other points. And we really liked that geometric pattern, and we wondered whether that could form the basis for the mesh for a roof. So if you remember, the kind of plan area of the roof is almost a square, so you could impose a square on this, and then imagine a roof. Now, as we all know, you cannot actually span a very large distance with kind of a flat structure. So the courtyard, the dimensions are about 30 meters by 30 meters. It's not quite a square, but those are the big dimensions, kind of. So this we cannot really span this with flat beams, because then the structure would get really deep and it would use a lot of steel and it would be very inefficient. So we extracted the mesh, the pattern which you see here at the top. There's a 2-dimensional extraction of the pattern that we found on the map, and we wanted to develop that into a 3D shape, into a cupola shape. And so basically for that we use a principle that Robert Hooke had discovered, that, you know, if you have a string and you let it hang, it will be totally in tension, and if you invert it, you get actually the ideal shape for an arch. But we use this principle in 3 dimensions, and obviously we didn't make a physical model like Robert Hooke would have done, but we used the algorithms that I had developed during my PhD to kind of develop this membrane type model that, you know, when you invert it, you end up with a cupola that is totally in compression and therefore very efficient, therefore uses very little steel, and therefore the economic and the environmental cost goes down. So fast forward a couple of years, the competition was won by Ney and Partners, and this design was built, and you see it here from a bird's eye view. It won a number of architectural prizes. Here's what it looks like when you lie on your back in the middle of the courtyard. And the cupola won a couple of prizes because there were many things that it did, but one of the things that it was really lauded for was its slenderness, and that is really, so basically how thin all the members can be, and that is basically really due to the form finding techniques that we use to develop the shape. So this is what it looks like during the day. At night, we inserted LEDs, and so this is what it looks like. And you can change the color of the lights. But what's important here, that it really, I think, makes you think of a starry night, maybe a starry night when you're on a boat sailing somewhere. So it really brings back this structure. It brings it back to the history of the historic building, you know, because it was used for these seafaring activities. And what also happened is that people come here because at lunchtime to eat their sandwiches, because they just think it's such a wonderful space. You know, they don't go into the museum. You know, you can go in free. If you're ever in Amsterdam, you should go in. You can go in free and have a look at the roof. But it's really, I think, wonderful if we can create spaces that are efficient, that are economic, but also that bring people pleasure. You know, people go there because they really want to be there, and it kind of makes their day a little bit better. I think then you are really working on very efficient civil infrastructure. There's also some other things that made me think that, you know, these kind of structures, it's an indeterminate structure. So that means that if you remove a member, you know, if one of these members breaks, the forces will find another flow through the structure. So it's very efficient in that way. Also, as I mentioned before, it has really good behavior. And because these forces are distributed throughout this grid shell, the whole structure kind of participates in taking loads. And so these are all very beneficial things to have in a structure. So that is the first project. This is a project from like 10 or 15 years ago, which, you know, I think is still very iconic and has achieved a lot of the aspirations that it had. I'm now going to move on to a very, very recent project, which was actually just published like a couple of weeks ago, and which has acquired a lot of media attention. As I mentioned before, some structures are just really amazing. You know, if you think about the pyramids, or this is another one, this is a Duomo in Florence. They're amazing on many, many different ways. One is, of course, their scale. Another one is that they have survived until now, right? So this dome is about 500 to 600 years old. It's still the same materials. This is in the north of Italy. You know, there are earthquakes there, and still this building still stands. And people still today come and see it because it's kind of really beautiful. And it reminds us also of how we can do things that last a long time and have a positive impact on the urban fabric. Now, for this structure here, I mean, there have been a lot of different amazing things that have been written about this structure, about how Brunelleschi, who was not really an engineer or an architect by training, he was like a goldsmith or a sculptor, you know, how he devised very innovative cranes to bring all the materials up to the dome. There have been records about how he built this dome without any scaffolding. And that is very interesting for me, because construction waste is enormous. If we want to do something about resources, limiting the natural resources that we use, we have to really start thinking about reducing construction waste. And especially for shell and dome structures, these structures usually rely on scaffolding and shoring and formwork. So basically, you first need to build the first structure, then you build the permanent structure, and then you take all the scaffolding and shoring away. And for example, with the formwork, a lot of the formwork ends up in the landfill. So people have been talking about, so the rumors have passed on that, you know, this was built without scaffolding, and there were some hypotheses how this is possible, but they were never really proven. And so in a study that we published this month, actually, in Engineering Structures, we show how these structures like this can be built because, and I'm going to show you the next slide, because of a pattern that you find in this dome. The Duomo is actually a double dome, and so the way it's built is first the first dome is built, and that then acts as a scaffolding for the second dome. And so we focus on the first dome. How can you make such a dome without any scaffolding? How can this, what we call, be self-centering or self-balancing? And what you see here is a picture not of the inner dome of the Duomo, it's a picture of an octagonal dome, but the principle is basically the same. So these domes were made out of masonry, so a combination of bricks and mortar. And what also really is very striking is when you look at the inner dome, but you might of course not see it because it might be covered with frescoes, but if you were to remove the decoration, you would see that there is actually a pattern on these domes. There is what we call a herringbone pattern. So there are like these spirals. So you have on the one hand horizontal layers of bricks, and on the other hand you have spirals that go up, in this case from the bottom of the crown all the way to the top. And you might think that these spirals are decorative, but actually we proved that they are really crucial in being able to build without scaffolding. I have to say that I didn't do this work by myself. I did this work with my collaborators from the University of Bergamo. So how does this system work? Well, so basically what happens is there's two things. One is that the domes were constructed always in horizontal layers. So only when one layer was complete, they would go on to the next layer. Now, in the case of the Duomo, this would take a long time because also the mortar would take a very long time to set. So that's why it took so long for it to be built. So that's one important thing. And the other important thing are these vertical bricks, which we call the herringbone bricks. And so this dome, you can imagine that you're building it, but from a moment when this dome starts like leaning inward, if you imagine that you're building a wall and you start to curve it, at some point it is going to collapse. So from the moment that these bricks want to start sliding inwards, something very interesting happens. And you can see that here. Basically what happens is that these bricks, the horizontal bricks, when they want to slide inward, they actually hit the vertical herringbone bricks and kind of get jammed in. And so in that way, they cannot really fall in anymore, right? So we have these horizontal bricks which start sliding inward. If there would be no friction, they would really fall in. But of course, because of the mortar, there's always friction. And so when they start sliding in, at some point, they get jammed in a little bit how you can imagine bookends, how they kind of squeeze these together, and that's how these bricks kind of get stuck. And then you complete the ring. There is also some kind of hoop action happening, and then you can continue doing this. And that is the way that they could construct these Renaissance domes in Italy with no use of scaffolding. It's kind of amazing also to see that for the Duomo, if they would have built wooden scaffolding, there wouldn't have been enough wood in Tuscany to build it. So there's also there's really a scarcity of materials there that kind of necessitated a really smart and clever way to build in such a way. And of course, I'm interested in this from a kind of curiosity, but also from a historic perspective. But also, I am very interested in learning either from history or art or craft or biology, where all kinds of systems have evolved over time, and see whether we can use them today. And so, as I mentioned before, this is a very interesting system. And I wonder whether we can use it to build shells or domes without scaffolding today. And so I had the amazing opportunity to work with SOM and the Create lab at Princeton University, that's a robotics lab, to see whether we could build a shell or a dome without any scaffolding. And we wanted to make it a little bit more complicated. We're going to make it out of glass bricks, and we're going to make it out of it would be built in a collaboration between humans and robots. And actually, this structure, not this structure, but the structure I will show you on YouTube. So that structure was built in London this spring. So it's a collaboration between humans and robots. And it doesn't require any scaffolding or any support. So it's a very efficient structure. It's a very economic structure. SOM was responsible for the form finding and the tessellation, and we kind of figured out how to make it stable through all the construction phases. And then the Create lab did all the path planning and tooling for the robots, and our students build it. So I'm going to show that video now.